Okay, this is lecture number 12 of EE 503, and today I would like to share with you a document on correlation coefficient. So let me start the share. So this is screen share. So this is our, let me see, course web page, and I'll be discussing this document. If you go to our course web page, you will see notes and correlation coefficient link. If you click on this link, you will immediately see the PDF file that I'll be talking about. Okay, so I have downloaded this. Let me start this file with the other reader. Okay. So today I would like to discuss one more time the correlation coefficient. So as you see, correlation coefficient between two random variables, x and y, is denoted as numerator, which is called covariance of x and y, divided by the product of what we may say standard deviations. And if you check this first sentence, it says that the correlation coefficient indicates the degree of linear dependence between two random variables, and I will be discussing this concept, linear dependence. So what we have seen earlier in the lectures, correlation coefficient, this definition, is in magnitude less than or equal to 1, okay? And if the correlation coefficient at the other extreme is equal to 0, you may say this is the minimum in magnitude, then we have the definition, a special definition, x and y are called uncorrelated random variables. Okay. Then at the maxima, in magnitude it is equal to 1. What we know is that, this is the interesting part, y is equal to ax plus b. In other words, x and y are random variables, and a and b are just constants. For example, y can be 2x plus 3. Okay. So this is the case. So this is an if and only if statement. If the correlation coefficient is 1 or minus 1, as you see. So this relation is called an affine relation. Affine relation is ax plus b type of relation. So this is a straight line, not passing from the origin because of this b. Okay. So what we see is that y is defined in terms of a straight line. If there are multiple variables, this will be an hyperplane plus some maybe a bias or shift. Okay, if we have multiple parameters. But what is interesting is the following. These two statements are equal. If I have, let me say, two random variables fully correlated, correlation coefficient of 1 or minus 1, that means that there is an affine relation between x and y. So here's another concept. Let's say that I want to predict y, but I only know x, another random variable x. So this is y hat is our prediction result. But as you see, this is a predictor, you may say, that is generating these predictions by processing x. Okay, so there's an equation like this, but as you see, this is also an affine relation. So this is ax plus b kind of relation. Correlation coefficient appears over here. Standard deviations appear over here. And these are the mean values for the random variables x and y. Okay, so this is a predictor for y. And we will be driving this, it's an optimal predictor actually, in the mean square sense, in our lectures later on. But as you see, given x, I can apply this for the prediction of y. Now, what is interesting is that if x and y are, fully predictable random variables, then indeed there is a linear relation between them, and this makes sense. Okay, given x, I can fully find y, so there is a zero prediction error. So if it is not, let's say, equal to 1 or minus 1, but it's a large quantity, let's say it's 0.99. So can I still do a good prediction or not? That is the topic. Okay. Well, here is the prediction error. So in other words, x-axis is the correlation coefficient. As you see, it is limited in between 1 and minus 1. When the correlation coefficient is equal to 1, y-axis is the prediction error variance. Again, we will be driving this later on, this expression. But what we see, as we have expected, When the correlation coefficient is equal to 1, I have a fully predictable random variables because they are fully correlated. Then prediction error is equal to 0 because there is an affine relation between x and y. When the correlation coefficient is equal to 0, so let's see, then my predictor, then this y hat becomes, this is 0, 0 times something, which is 0, plus mean of y. So my prediction is only mean of y, okay? So it's independent of x, as you see. So this is prediction. So my error is y minus y hat. So that means that y minus the mean of y. Then its variance is the variance of y. So as you see, this is the worst case. If random variables x and y, they are uncorrelated, then I see a large prediction error. And this prediction error is equal to the variance of y. Again, we will be deriving this, but this is also telling us something that, this correlation coefficient is an important criteria in terms of prediction, as you see. Here is a MATLAB code generating this figure, just for your information. Now, I would like to understand this a little bit further. What do I mean by that? Now, I'm assuming that y is equal to x plus some noise. Okay? So I'm generating x from a distribution, generating n from a second distribution, and x and n, they are independent. Then I'm generating a y by adding up these two samples, x sample and n sample, and that will be the generation of y. As we have seen in the earlier lectures, correlation coefficient between x and y generated in this fashion, is written in this way. Okay? So this is square root variance of x divided by sum of the variance of x and n random variables. Now, let me see. If, correlation coefficient, this number, is set to 0.999, okay, meaning that I have a fixed x random variable, this is not changing, but I'm changing the variance of noise, okay? So the variance of noise is changing. So I'm adjusting the variance of noise such that correlation coefficient is 0.999. X is it's a uniform distribution in between 0 and 10. Okay, it acts as a fixed random variable, fixed random distribution, I should say. N is Gaussian noise added over X, and its variance is adjusted such that correlation coefficient is 0.999. So what do we see? For example, if X is selected as 5, then I see that Y is, so what is this experiment? I repeat this, Y is equal to X plus N, maybe 1,000 times. So I pick an X, pick an N, add them, then put a mark on XY plane, okay? Then I repeat this marking 1,000 times. So let's say that around X is equal to 5, Y's are, as you see, they are limited to a very small interval. Indeed, you can see that this is a straight line. Y is equal to X line. So if you repeat this experiment, you see that if the correlation coefficient is 0.999, X and Y cannot deviate from each other too much. And they are, as you see, they are on this, mostly located on this straight line. Y is equal to X line. So this is for the 999 case. Now, if I have 0.99, what I see is that for X is equal to 5, now there's some spread. Okay, so this can be maybe 5.5 over here. This can be 4. Or this can be 4 over here, as you see. So you see that there is more spread right now over here. So because noise variance is right now higher, so I see that there is more deviation from this straight line. 0.9, now you can see spread is even further larger for a fixed, let's say, X is equal to 5 case. But still, there's lots of predictability. For example, if you see that Y is equal to 12, now, what does that mean? In that case, you are sure that X is in between, let's say, 8 and 10 in these experiments. If Y is equal to -2, you see that X is equal to, let's say, 0 up to maybe 3 and so on in these experiments. So still, you can say lots of things. It's not totally random. So you see the trend also over Okay. 0.5, again, we see a trend. So you see that these parts are empty, meaning that if I have a small x value, noise will not be making it very large, as you see. Added noise will not be changing, after this summation. Y will not be having, significantly large values. So there is still a trend, and this trend is making the prediction actually. So this is the case when x and prediction possible. X and y, the correlation coefficient in this case is 0.5. So 0.25. So as you see, this range is right now minus 40 to 40. X range is 0 to 10, like in all other cases. So for x is equal to 5, I see minus 25. So some other sample at 22, you see that there is a large spread. And I'm losing this trend a little bit, okay? 0.01. So as you see, it's almost like uncorrelated. So given x, y is distributed in a wide range. If I go to a higher x value, let's say 10, I see almost like a very high range. So you see that if this correlation coefficient is 0.01, let's say 1%, then the knowledge of x is not very useful in the prediction of y, because for y is equal to 400, you see that all of these x's, 0 to 10, it seems that there are some cases that has already occurred in this random experiment. So what's my comment? So this correlation coefficient tells us about the predictability and what I will call later on the linear dependence between two random variables. So for example, 0.75, it becomes a figure like this. You'll see lots of predictability. Okay, so let's go back to, let's discuss the MATLAB code for this. This is called the scatter plot. So I'm generating x random variable, as you see, from uniform distribution. Run test generating a uniformly distributed, let's say, sample from a uniform distribution in 0 and 1. If I multiply it, this becomes multiply by 10, this becomes a sample taken from uniform distribution in between 0 and 10. So I generate x 1000 times. Okay. Desired correlation coefficient is 1/4. So maybe you can remember, sigma x square. So what is the variance of this x random variable, this uniform distribution? Maybe you can remember this. This is called delta square over 12, where delta is the support of the uniform distribution. So this is in 0 to 10. So delta is equal to 10. So 10 square over 12 is the variance of x random variable. Then the variance of the noise is adjusted such that I have the correlation coefficient of 0.25. Okay, sigma n square is the variance of the noise. Now I have then y is equal to x plus, this is noise, and rand n is Gaussian distributed random variable with 0 mean and unit variance. And if I multiply this by sigma n square root, I get a Gaussian distributed random variable with 0 mean and sigma n square variance, where sigma n square is adjusted to have a desired correlation coefficient. And then I plot x and y values and put a mark, put a cross at the xy location. And I repeat this for all of these samples. This becomes the scatter plot. Now we have fully understood this experiment. Now we have fully understood how I can have such a case, and so on. Okay. Okay, now that's all I would like to say, but here is a warning. Now, to understand the linear dependence, maybe we should focus on a nonlinear dependence case. What do I mean by this? Nonlinear related random variables and correlation coefficient. So let's assume that y is mapped to x with such a nonlinear relation, ax squared minus bx. So between x and y, as you see, there is nothing random. So if you tell me x, I tell you y with perfect accuracy. So there is nothing, there is no noise effect over here. Now, can I calculate the correlation coefficient of this x and y? Of course I can. This is the definition. So let me try to. So the product of x times y is expected value of the product is calculated. X times y is equal to, as you see, ax squared minus bx. So if I operate this, I get something like that. So in this case, what is x? As I have said in the earlier cases, x is uniformly distributed in 0 to delta. In the earlier example, delta was set as 10. Maybe you can remember x-axis was from 0 to 10. So I'm again assuming something like that, but I'm just writing here delta, not 10 over here. Okay. So then expected value of x, uniform distribution is delta over 2. Expected value of x squared, x cubed is easy to calculate. Now, if you do that, expected value of the product of x and y is something like this. Now, for the correlation coefficient, what do I need? I need the covariance of x and y, which is the numerator term. Okay, expected value of xy minus the product of the means. So if you calculate the product of the means and do the subtraction, you get a result like that. So what's interesting is that from this Ross relation, I can make this covariance of x and y equal to 0 if I select a and b as a over b as 1 over delta. If delta is equal to 10, let's say, if I select a as 1, b as 10, then the correlation coefficient between x and y becomes 0. Okay, so this is a little bit, you may say, surprising because x and y are deterministically related. So given x, y is perfectly predictable, but not in a linear sense, I guess, because you see their covariance is equal to 0. So let me emphasize this. Now, in this plot, there are two scatter plots. So the blue one is as before, y is equal to x plus n. X is uniform distributed in 0 to 10. N is noise is adjusted such that in the blue one, correlation coefficient is 0.99, okay, like in the earlier cases. So I am adding the same amount of noise to the other non-linearly related random variable, okay? Y is equal to, as you see, there is a non-linear relation, plus noise. So obviously, there is same amount of deviation. This is a quadratic curve. There is an identical amount of deviation in the linear case and in the quadratic case, but unfortunately, as we have seen, even without the noise, covariance of x and y is equal to 0. Since over here there is n is also independent from x, this noise is also not helping to increase the covariance also. So as you see, this red part has, let's say, covariance or correlation coefficient equal to 0, even though it seems to be very well predictable with a nonlinear predictor, isn't it? Satisfying this quadratic kind of relation. So about this 0.9, well, we see the same spread, but since, well, this is a quadratic case, it seems to be uncorrelated. So this is like a surprising result. So if x and y pairs are not linearly dependent, let's say in a loose sense, then this correlation coefficient does not tell us the truth. It does not tell us the predictability of two random variables x and y. Okay. Okay, so this is the MATLAB code for this part. But before the MATLAB code, I would like to go back to the very first slide, very first page. Maybe you will remember the correlation coefficient indicates the degree of linear dependence. So this is what I mean by linear dependence of two random variables, okay? So if there is a nonlinear relation between two random variables, unfortunately correlation coefficient or covariance does not tell us, it does not tell us useful information in some cases. But in general, we are happy. Let's go back to the end. In general, we are happy what the covariance provides us because we will be doing mostly linear processing. Okay, for the linear processing, we will see covariance, correlation concepts. They will be extremely useful. So how do I generate this? Well, almost like the same. Please examine this MATLAB code. In addition, so in the last two lines of this MATLAB code, I am also verifying the correlation coefficient. Like this is, the blue case, the linear case. In this case, correlation coefficient turns out to be 0.9. In the red case, the nonlinear case in the plots, blue and red, you see it's almost like uncorrelated. Okay, that's all I would like to say. And we will be continuing with more discussions on the correlation coefficient in our lecture hour. Thank you very much.